Hey everyone. Um, I know that today's lesson was on radiation, and while you took the notes, you may not have totally understood what was going on. So, what I want to do with this video here is just run you through a couple of practice problems so that way you have an idea of how the information that you took down or should have taken down fits in with how to actually apply it to a nuclear reaction. Because that's what we're doing now. This is what's called nuclear chemistry. All right. We're going to start with alpha. Now, again, just so you know, alpha is the heaviest type of radiation. It has a positive charge. In fact, it's the alpha particle itself is going to have a +2 charge, just so you know. And we represent that by using this 4,2He. Okay, because an alpha particle is made up of 2 protons and 2 neutrons. Now, how does that work? Well, the first thing we have to remember is we are dealing with the law of conservation of mass. That means that mass is going to be conserved. And when I say mass, I'm referring to this number up in the upper left corner, the mass number. All right? Now, in alpha radiation, the minute you say something undergoes alpha decay, the thing to remember is it's going to be a positively charged particle and that it is helium or 4,2He that is breaking off. While you can use the alpha symbol, okay, and the alpha symbol, remember, is this one right here, the little some call it a fish swimming to the left, but anyway, it's the alpha symbol. I prefer using this because it helps deal with the conservation that we were just mentioning. All right, so we started out with uranium-238. It has a mass number of 238, 92 protons. When we do it, 2 protons and 2 neutrons break off. And remember that the protons and the neutrons are what give the mass to an atom. So that means we have our alpha particle plus our remainder, okay? What remains of the whole after this leaves. So what we're going to do here is we're going to take 238. Well, 4 broke off of it, minus 4. That's going to give me 234. Well, that's going to be the mass of our new atom. Because again, since mass is conserved, we started with 238, we better end up with 238. So 4 plus 234 is 238. If you remember correctly, protons define what the element is. So in this case, what that means is we started off with 92 protons. However, the alpha particle, 2 protons broke off of that. That means our new element, or our new number of protons, is 90. So this is how I got my new numbers. So 90 plus 2 equals 92. 234 plus 4 equals 238. So everything's conserved on both sides. But because the proton defines the element that you have present, we now have a new atom here because we only have 90. So we literally went back so we go from 92 to 90, and when we look on the periodic table, that is thorium, Th. Okay? So that's how we go from a parent atom into the resulting products, as it were, when the nucleus splits up for alpha radiation. That is not the only way these questions can be asked, however, and that is something to pay attention to as we proceed forward. I can give you the end results as well and ask you what was the original atom these came from. In this case, we did some subtraction to figure it out, to go one way. So, and to go backwards, we're simply going to re-add everything. In this case, I have a mass number, so we'll start with the mass numbers. We have 181 with the tungsten. We have 4 with the helium. Remember, these were all part of one atom at one time. So the 181 plus 4 is 185. So that was our original mass, going backwards. Well, we have 2 protons. Now we come down here again to our atomic numbers, the number of protons. We have 2 protons here, 74 here. So 74 plus 2 equals 76. So that means we originally had 76 protons in a given atom. When we go and look at our periodic table, we find out that is osmium, OS, was our original atom. Okay, so just a quick rundown on how to go forward and backwards for alpha radiation. Beta is the one that a lot of people tend to struggle on. All right, so we're going to go to beta next. All right. Once again, you can use either the electron or the beta because that is the particle, the beta particle or the electron. In this case, it kind of doesn't matter. All right. But remember, the beta particle has a charge of -1. All right. And it's caused by a neutron that splits down into a proton and an electron. What that means is when the neutron breaks down, we add a proton. So we take a look at our PNE. Here's where the PNE comes in. So for carbon 6, okay, so for carbon 14, we have protons, neutrons, electrons. Now, in all honesty, we really don't need the electrons here, so we're just going to focus on protons and neutrons. Well, we start off with 6 protons. Well, protons plus neutrons equals our mass number 14, so that means we had 8 neutrons. If you remember correctly, the protons and neutrons have all the mass of an atom. They both weigh 1 AMU, 1 atomic mass unit each. So when the neutron breaks down, we're losing a neutron. Subtract 1 here. Okay? However, the neutron turns into a proton, so we're adding a proton. That means our new numbers become 7 and 7. 6 plus 1. All right. So the first thing I'm going to write over here is my beta particle, the electron, or again, you can use the beta symbol. And our new numbers are 7, and 7 plus 7 is 14. So our mass number is 14. You'll notice we started with a 14 up here for beta, we end with a 14 up here for beta. It's one of the really nice things about this is that when you're undergoing beta decay, the mass number for the starting parent atom and the atom that's produced is going to be the same. The number of protons, however, goes up by 1, so we went from 6 to 7 in this case. All right? All right, so we look up 7. 7 is a new element because the protons define the element, and 7 would be nitrogen. Okay, so that's how we go from there. Now going backwards, you have to be able to recognize this means we underwent beta decay. Okay, it's the fact that we produced an electron like this. We're going to do the exact opposite. All right, so we have so now, like last time we saw, mass number before and after stays the same for beta decay. So we end with 195, we started with 195. All right, but this time we're going to go the opposite way, backwards, which means we're going to subtract 1 from 79. So 79 is our end result, which means we went up by 1, minus 1 proton, which means 78 is where we started. That means our original atom was platinum. Because again, the atomic number or the number of protons defines what element we have present. Lastly is gamma. Gamma is the simplest of all the types of radiation, because literally before and after are going to be one and the same. So this and this are identical for gamma. But we also get energy, or the gamma symbol. So this represents energy. But in essence, there is zero change to that atom. All right? So we come down here. If we want to go backwards, if we want to go in reverse, well, first we're going to identify the type of reaction that's occurring. In this case, we look at our results. Well, we got gold, and we have this symbol here. This is gamma. The minute we see the gamma symbol, we know that what we ended with is what we started with. And you are done. Okay, so this is the essence of step by step for the different types of radiation and how to go about them. Now, as a quick reminder, the thing we got to understand is we are following the law of conservation of mass. Okay, and now we're talking about the mass, we're talking about the mass numbers here. So that means the mass number on the left-hand side has to be equal to the total mass numbers on the other side. All right, as you saw, for gamma, for the gamma reaction, we saw we had 195, and it was 195. For beta, okay, again, kind of coming back here to our examples. Okay, we had 195, we had 195. It stayed the same. Beta is also the same. All right, we started with 14, we ended with 14. Okay, so that's the nice thing about those two. The only one we have to worry about doing any sort of addition to that is with the alpha. So we started with 14, we ended with 14. Alpha, well, in our case, we started off with 238 for uranium. We created the helium particle, or the alpha particle, which is 4, mass number 4. And whatever remains goes with our other atoms, so that was 234. As you can see, 238 equals essentially 4 plus 234. So the mass numbers are the same. Same thing with the protons. We started with 92 protons here. We had 2 with our alpha particle plus 90. Well, 90 plus 2 is 92. So that's how the law of conservation of mass comes in to help assisting you with this. All right, that's it for this particular episode. I will hopefully be back soon to help you with some more.